Hello guys, welcome to my video. So today I'm going to be solving the physics paper 2 for May June 2023 paper 2-1. Okay, so please like, comment, share and subscribe, and please share if you have any comments or any queries or anything that I can do to improve the content. Okay, so let's start. The first question is asking us to define power. So power is basically the rate of doing work, right? So how fast are you doing something, right? So basically it's just the work done per unit time. Okay, so power is the work done, okay, the work done per unit time. Okay, and you've been asked to use that definition of power to show that its SI units are actually kg m squared s to the power of -3. Okay, we know that power is equivalent to work done over time, right? Therefore, the units of work done, right? The units of work done will actually be equivalent to kg m squared s to the power of -2, because work done is force multiplied by displacement, right? And force is kg ms to the power of -2, because force is mass multiplied by acceleration. So work done will be kg m squared s to the power of -2. So the units of work will therefore be equivalent to kg m squared s to the power of -2, and the time will actually be the second, right? So the total will be kg m squared s to the power of -3, right? So remember, if the question says you must show, you have to really show what the units mean, right? So the first mark that you get is for you knowing that this is an expression for work done, and these are the units for work that you have, okay? And then for giving this correct expression, you'll be able to get the answer. Okay, moving to the next question. The intensity of a sound wave moving through a gas is given by that equation, right? And we also determine the SI base units of K. Whenever a question asks you to determine the SI base units, make that thing the subject of the formula. So K is actually equivalent to I over F squared A squared, right? So the units of K, okay? So the units of K is equivalent to the units of I, okay, over the units of F squared A to the power of -2, right? So F squared A squared, right? So these units and that units will basically be the units of K. But how do we find the units of intensity? We know that intensity is basically the power per unit area. So in physics, intensity basically refers to how much power have you applied per certain area. And power, we've calculated its units to be kg m squared to the power of -3 in the previous equation. So the units of intensity, right? So the units of I will be equivalent to kg m squared s to the power of -3 divided by m squared, right? So divided by m squared, and that actually gives you kg s to the power of -3 as the units of intensity, right? The units of F, right? The units of frequency, remember frequency is 1 over t, right? So the units of F will actually be per second, right? And the units of amplitude is actually measured in meters, right? So the units of amplitude will actually be in meters, right? So the units of K will be kg s to the power of -3 divided by s to the power of -2, because it's squared, m squared, right? So this would be kg s to the power of -3. Okay, so our value of F is actually s. Okay, so sorry, we forgot the v, the velocity. Okay, so your velocity that is there at the bottom multiplied by the units of velocity. Okay, so your velocity over here, right? And the units of velocity is ms to the power of -1, right? So this becomes kg s to the power of -3 plus 2 plus 1 m to the power of -3, right? So 2 plus 1, that's 3, and it's in indices, it's m to the power of -3. So this gives you a total of kg m to the power of -3. Okay, so what are they looking for, right? They're looking for these units, right? So can you be able to find the units of intensity? Do you know that intensity is power over per unit area? They're also looking for these units themselves that are correct, right? For frequency, for amplitude, and for velocity. And lastly, they're looking for this answer that you're going to give, which is the units of K, which is kg m to the power of -3. Moving on to the next question. When we're given a uniform beam, right, of weight W that has been connected to a fixed support, right, like that, and it is and a compressed spring is extending a total force of 8.2 newtons, right, vertically upwards, right? So how is this string working? It's exerting a force upwards that is of 8.2 newtons, right? So 8.2 newtons over there, right? And we've been asked to show that the vertical component of the tension is 2.4. How do we show this? Well, the one just has to give their answer. So we have to resolve that force into two components, right? So into this component, which is 4.8 sine of 30, right? So very important. So that component will be equivalent to 4.8 sine of 30, and that gives us a total answer of 2.4 newtons, okay? Right. By taking moments about the hinge, determine the weight W of the beam, right? So the weight, this weight W of the beam itself, right? So the principle of moments states that the summation of the clockwise moments will be equivalent to the summation of the anti-clockwise moments, right? So if a beam is moving in a clockwise direction, those forces will be equivalent to the summation of the moments in the anti-clockwise direction, right? So those two different moments should be equal. So if we were to look at the clockwise, like a watch, the clockwise moment is all the moments that are moving in that direction, as you can see on the screen. So if we look at those forces, we have one force, which is 0.30, right? So that force, which is acting in that direction, right? And we also have this force, again, acting in that direction, right? So we have to be very careful. This is our hinge, and all the forces acting in that direction will be equivalent to one force that will be acting up. So let's start with the clockwise moments, which is the first one being W, right? So it will be W times the distance of 0.60, right? So W times this perpendicular distance from the pivot itself, right? 0.60, and you have 0.30 plus 0.30 multiplied by this distance, which is 0.50 plus 0.10 plus 0.20, right? So that gives us a total of 0.80 plus another force, which is that one of our tension, which is 4.8 sine 30, which is actually 2.4, right? And the total distance, if we were to add up this whole distance, that's actually okay, so it's 0.5 plus 0.1 plus 0.2 plus 0.4, that's actually 1.2, right? So this will be 2.4 times 1.2, and that must all be equivalent to our anti-clockwise moments, which is only one in this case, right, which is 8.2, right, and 0.50 from the pivot, right? So we have 8.2, right, and 0.50 from the pivot itself, right? So these two forces must actually be equal, right? So the forces which are acting in this direction must be equal to the forces acting in that direction, right? So let's look at these forces. So how do you find the value of W itself, right? So W will be equivalent to, okay, so W will be equivalent to 8.2 multiplied by 0.50, right? We subtract 0.30 multiplied by 0.80 plus 2.4 multiplied by 1.2, and we divide by 0.60. So that gives us a value of W, which is 1.633, which is 1.6 newtons, right? So it's 1.6. So I'd really highly recommend that you break down these calculations so that they become so much easier for you to understand, and you avoid making errors during your calculation. Again, what are they looking for? Well, they're looking for you stating these different components themselves. They want to know if you know these independent components that are present, right? Any one of them really can get you the first mark. And the next one is they want you to know this law of summation clockwise moments is equivalent to anti-clockwise moments. And the next one, they just want you to then calculate your weight, which is 1.6 newtons acting downwards. Okay, so they've asked us to calculate the horizontal component of the force exerted on the beam by the hinge. Now, whenever we say equilibrium, we mean that there is no resultant force. We mean that there is no resultant torque in any direction whatsoever. So if we look at our beam, this string, as you might see, has actually a horizontal component in that direction, right? Which is T cos of 30, right? But there's nothing that is counteracting that force, meaning that this beam has to exert a horizontal force that counteracts that force of T cos 30. So the horizontal component of the force exerted on the beam by the hinge will then be equivalent to T cos 30, and that would be 4.2 newtons, because that's actually 4.8, okay, 4.8 cos of 30, right? So our answer is 4.2 newtons, right? The spring obeys Hooke's law actually and has an elastic potential energy of 0.32. Calculate the compression of the spring. What is Hooke's law? Well, Hooke's law says that the force applied is directly proportional to the extension, meaning that provided that the elastic limit is not exceeded, meaning that F is actually equivalent to Kx, right? So if I have a graph like that, which is a force against extension graph, the area underneath this graph, right? So that area, right, actually represents elastic potential energy, right? So this actually represents elastic potential energy. So the area underneath a force extension graph represents elastic potential energy. But this is a triangle, remember. So the area would therefore be half times F times X, right? So basically, if I want to find the compression, I know that the elastic potential energy is equivalent to half times the force times the extension, right? The elastic potential energy, 0.32. Half, what is my force? It's 8.2, right? So my force is 8.2. And I want to find the value of X, right? So 2 times 0.32 divided by 8.2, that is my value of X. So my value of X will be equivalent to 0.078 meters, right? So 0.078. So remember, elastic potential energy is the area underneath a force extension graph, and it's actually equivalent to half Fx, half the average force times the value of X, right? So find your force and find your extension. So what are they looking for? Well, they're looking for you to give them this equation themselves, right? So if you don't state this, if you just calculate without telling them that I know that the elastic potential energy is half Fx, you won't get your mark. And the other mark comes from the answer itself, okay? The string is then cut so that the spring extends upwards. So as the spring extends upwards, it launches the block in the air, right? So this is a block, okay? So this block is launched in the air, right? And the block reaches its maximum height, right? So its maximum height is somewhere over here, okay? So this is its max height, right? Then it begins to fall, right? Then it falls back to the ground, right? So it's starting at A and then at B. So we've been asked to calculate the decrease in the gravitational potential energy for its movement from A to B. Okay, so the first thing, right, I always say, state the formula. Whenever I'm seeing this question, I'm thinking of one formula because the question has told me of gravitational potential energy. The formula that must come to mind is delta GPE is actually mg delta H, right? So this is very important formula that you must know firsthand. What is the mass of this block? 0.3, right? Because I already know that it's 0.3 newtons, right? So the mass of here, the weight rather, will be 0.30, and the height is actually 0.090. So the total will be 0.027, right? So 0.027 is actually my decrease in gravitational potential energy. So it had a certain height at A, and all of that height is going to decrease to 0 when it arrives at point H. And that means all the gravitational potential energy has actually decreased to 0 as it arrives at point B. The next one, we've been asked to use the law of conservation of energy to determine the speed of the block at point A. So what is going to happen? At point A, the block actually has a certain amount of energy. But as it is arriving at point B, according to our question, the elastic potential energy at B will be equivalent to the kinetic energy at B will be equivalent to the kinetic energy at A and the gravitational potential energy. What do I mean by this? Well, this thing is not stationary. As it's moving at A, it possesses a certain kinetic energy, right? And it also possesses a certain gravitational energy, okay? And this is due to these two particular energies that are present at point A. But as you arrive to point B, all of that energy disappears only to kinetic energy, right? So all of the gravitational energy has been converted into kinetic energy at point B. So the first defining equation that I can give is that the kinetic energy, okay, the kinetic energy at B rather, is equivalent to the kinetic energy, okay, at A, right? Kinetic energy at A, plus, right, the gravitational potential energy at A itself, right? So at A, we have those two kind of energies that are sort of coexisting. So I want to find the kinetic energy at A itself, right? So the kinetic energy at A, right? So the kinetic energy at A will be equivalent to the kinetic energy at B. So this kinetic energy that we have at B, right? So this kinetic energy at B, right? So the kinetic energy at A will be equivalent to the kinetic energy at B. Okay, so the kinetic energy at A will be equivalent to the kinetic energy at B. So kinetic at B, right? Because we've just made substitute formula, subtract the GPE at A. So the kinetic energy at B, we've already been told that is 0.044. So 0.044. We subtract 0.027. Okay, so we subtract 0.027, and we end up with an answer of 0.017 joules, right? But kinetic energy, right? But kinetic energy is actually half mv squared, right? So how do you find the speed? The question wants me to determine the speed. So always ask yourself, right? You visualize the question, ask yourself, what does it want me to find? It wants me to determine the speed that is there, right? So we go here, right? We then say the kinetic energy, I now have it, right? Which is 0.017, right? So how do I find my speed? Well, I just need the mass of the object itself, right? So how do I find the mass of the block? We know the block weighs 0.30 newtons. So how do you find its mass? Well, so it's just be 0.30 divided by 9.81, right? Times v squared, okay? So if we were to take this calculation here, so basically, the value of v would therefore be the square root of 0.017 times 2 times 9.81 divided by 0.30. Again, I would very much advise you to break down these calculations so that you get the accurate answer as possible, right? So your value of v would therefore be equivalent to 1.1 meters per second, so 1.05. That's equivalent to 1.1 meters per second. So break down the calculation so that you can be able to answer the question accurately. Okay, so the next question, by reference to the force on the block, explain why the horizontal component of the velocity of the block remains constant as it moves from A to B. Okay, so why does that remain constant? Why does that a horizontal component of the velocity remain constant due to its motion? Well, because the weight is vertical, right? So since the weight is vertical, okay, or the resultant force, right, is vertical, no force acts in the horizontal, right? No force acts in the horizontal. Hence, this means that although the forces that act in horizontal do not exist, hence it will remain constant. Remember, a body remains at its constant rest or uniform motion unless acted upon by an external force. Okay, moving on to question IV, we've been asked to show the graph of the variation of the magnitude of the vertical component Vy of the graph from time t is equals to A to t is equals to B. Okay, so whenever you're given a question that asks you to sketch a graph, you must think of two things. You must think, rather three things really. Whenever you see graphs, you must think number one of axis. The second one, you must think of gradient. And the third one, you must think of area underneath the graph. You don't need really to satisfy all three, but you just have to be thinking of them, right? So here I'm given the vertical component of the velocity, and here I'm given the time itself, right? So if I'm moving from A to B, right, you'd acknowledge that my velocity has to increase, right? Even if you look at the kinetic energy at A, it's usually 0.04, meaning that it's greater than the kinetic energy that it has at A. So the kinetic energy at B, is greater than the kinetic energy that it once had at A, meaning that this object is actually speeding up, right? But the question has already told me that the horizontal component is remaining constant, meaning the only thing that really changes is just the vertical component of the velocity because of that weight itself. The thing is going to accelerate downwards because of the weight that is causing it to fall down. So this velocity is going to actually increase, but it's not going to start at 0. Remember, at A, it already has some kinetic energy. So the velocity is going to start at a non-zero value, right? So it's going to start at a non-zero value, but it's going to just increase uniformly because your gradient is actually the same, right? So basically starting here at a non-uniform value like that, right? Because your gradient is already the acceleration, so it must remain constant throughout the motion, right? So what are they looking for? Well, they're looking just for a straight line with positive gradient. So if you give them a straight line, that is positive gradient, right? That's positive gradient, and the line that is starting at a non-zero value of V. So it's a non-zero value of Vy, they'll be very happy. I just want to see if you really know what it means to say that the velocity is given. Right? This question could have started from the maximum height. Your graph would have just started from the origin. But here, because it already has some velocity, we're not going to start at a zero value of V. Okay, moving on to question number 3. When we're given a block that is pulled in a straight line along a rough horizontal surface by a varying force Vx, right? So we've been told to assume that the air resistance is negligible, and we've been given the variation of momentum against time, right? Remember, I always say, analyze a graph based on 3 things, right? The first one, look at axis, right? The second thing, look at the area underneath the graph, right? Look at the area underneath the graph. The third thing, you can look at the gradient, right? The order doesn't really matter. So axis, gradient, area, just those 3 things, right? So whenever you see a momentum time graph, remember this, right? A momentum time graph, the gradient represents the resultant force, right? It's not just any force, it's the resultant force. In this case, the resultant force is actually this force X, right? Since it's moving along a rough horizontal surface, subtract the force of friction that will be acting in that backward direction, right? So that is basically the resultant force itself, right? But let's first start with the question before we get to answer anything else, right? So the first question is state Newton's second law of motion. So they just want us to know, they just want to test us and see if we really know Newton's second law of motion. So Newton's second law of motion states that the resultant force, okay? So the resultant force, right? Acting on an object, right? Acting on an object is proportional, okay? To the rate of change of momentum, right? To the rate of change, okay, of momentum, right? So this is what basically Newton's first law says, right? If you have a resultant force acting on an object, that resultant force is proportional to the rate at which the momentum of that object is changing, okay? So for the time at t is equals to 0, we've been asked to determine the resultant force acting on the block, right? So we've been asked to find the resultant force that is acting on the block when t is equals to 2.0. So let's go to 2.0, which is somewhere over here, okay? So here, this, remember, like I said, right, this gradient, right, this gradient itself represents the resultant force, right? So this gradient tells me something about the resultant force, right? So if I find this gradient, I found the resultant force. This is from 0 up until 4 seconds. That force is going to always remain constant, right? So how do I find the resultant force at this point? The resultant force is actually the gradient, right? So the gradient, right? So resultant force is actually delta P divided by delta T, so which is actually equivalent to your gradient, right? So how do you find our gradient? What force do we have, right? From here up until there, it's still just constant, so we can just say 6 over 4, basically. So we can just say 6 over 4. That is actually equivalent to 1.5. Right, so that is basically our resultant force. and we've been asked to find the force X, okay? But remember, like I've said, the resultant force is actually the force X, right? Subtract the force of friction. Do we have the force of friction? Well, we actually do. If you look at the question, it said that the frictional force is a magnitude of 2.0, meaning that this friction is actually 2.0 newtons, right? So if we were to go here, right, the value of force X, right, so the force X will actually be equivalent to 1.5 plus 2.0, that would be equivalent to 3.5 newtons. So that is the total amount of force, that is force X exerted by this this ball. Okay, the last question involves to sketch a graph for the variation of force X with time t from t is equals to 0 to t is equals to 0.6. Again, I asked you guys, what does a graph tell you? Look at the axis, look at the gradient, look at the area. So this graph, really, the area doesn't tell us much because it's just a force against time graph, right? The gradient, again, really doesn't tell us much because it's actually the resultant. It's not exactly the resultant force, it's the force X itself, right? But basically, let's look at the times, right? From 0 until 4, what is my value of my force R? From 0 until to 4, we've calculated the value of force X to be actually 3.5, right? So from 0 until to 4, the horizontal line is actually at 3.4, right? So if we were to go at 3.4, so from t to is equals to 0 up until 3.4, we actually take this value of 3.5, right? So it's actually this force that we have up until that point itself, right? But from 4.0 to 6.0, right? So I want you to look at this, right? The resultant force here is 0. Remember, if gradient is 0, right? So since gradient here is equivalent to 0, the resultant force is also equivalent to 0. But if I have a frictional force that is pulling me backwards and a force X that I'm applying forward, if resultant force is 0, it means that these two forces are equal in magnitude, right? So it means that the force X, when I have right from 4 to 2, now has to be 2.0, right? So this force is not really 0. It's actually the force now, which is 0, which is here. So it is decreased here, right? So basically, you're done with your graph. So what are they looking for, right? So they're looking for from t is equals to 4.0 to 6.0, right? They're basically looking at a horizontal line. So they want a horizontal line at X is equivalent to 2.0 newtons, right? So you get your mark here. And again, from t is equals to 0 to 4.0, they're looking for a horizontal line. Again, at X is equivalent to 3.5. You get your mark here. The other one was just a lenient mark, right? They're just looking for any horizontal line at any non-zero value of X, right? So you just get your mark if you just drew a horizontal line, right? But I would urge you, ask yourself, what is my axis trying to tell me? How do I interpret the graph? And how do I come up with an accurate response to answering this graph, okay? Moving on to question number 4. We've been given a liquid with a certain density, and we've been asked to, with a certain density, right, pressure, and we've been asked to prove this formula. Show that pressure is equals to rho GH, right? Very important formula for you to prove. Okay, so let's first start, right? The first one, we know that pressure, right, is actually force per unit area. Okay, this is something that we know, right? But density, okay, is equivalent to mass per unit volume, right? So the mass is actually the density times the volume, right? So the mass is actually density times volume, right? But force, this force is actually mg, right? Because this liquid itself has a certain force, right? So this whole liquid has a certain force that is exerting, right? So the whole liquid itself has a certain force that will be exerting, which is mg, right, on the base area, which is over here, right? So this will be a value of mg. So the force will be mg divided by a. But we say that m is actually equivalent to this value, so we substitute that value, right? So that would be your density times v times g divided by a, right? So, but volume is actually area times height, right? So if you have a certain shape, if you want to find its volume, it's area times its height, right? So this particular density, right? So it will be rho times a times h times g divided by a. Those cancel out. So the pressure will actually be rho gh, right? So it's shown that is equal. So what are they looking for, right? Number one, they're looking for this definition. So if you give them the definition of pressure, they'll be very happy and they'll award you 1 mark. If you give them the definition of density, you get another mark. And the other one is the appropriate algebra, all of this that we have done until we have arrived to this answer. That will be our last mark, okay? Moving on to the next question, we've been asked to suggest why this equation does not give us the total pressure on the base of the beaker. Remember, this is only the pressure due to the liquid itself. But the air is also exerting a certain pressure. It's also causing a force, right? With the whole atmosphere that is over here, that is exerting a force down on this liquid, right? So that whole atmosphere is also going to cause a certain pressure on that base area. So this equation does not give us the total pressure. Why? Because there is also, right? There is also atmospheric pressure that is not accounted for. There's also atmospheric pressure that is not accounted for. Okay, very important. Right. Moving on to the next question. We've been given a variation of pressure against the depth x of the graph, and we're asked to determine the density of the liquid. Right. What do we know? We know that pressure is actually delta H rho times G, right? So if I have a density, a pressure against an X graph, right? So that's basically this graph itself, right? Against rho G delta H, right? So it's these two variations. That actually means that this is actually my gradient, right? So the gradient of this graph is actually rho times G. So how do I find the gradient of this graph? Well, identify any 2 points that I want. For example, this point and that point, right? And the gradient of this whole line, right? The gradient of this whole line itself actually represents the density of the liquid itself, right? So if I've identified these points, that means the gradient will actually be equivalent to delta rho over delta H, right? So what is my density difference in pressure? So my difference in pressure, like I've identified those 2 points, will be 9.66 subtract 9.60, right, times 10 to the power of 4, right, divided by my change in height, actually 8 times 10 to the power of negative 2, subtract 0, right? So that gives me a gradient of basically this whole thing, right, that is equivalent to so that gives me a total gradient of about 7,500, right? So rho G actually represents 7,500, right? So rho G is actually equivalent to 7,500. So my value of rho will be 7,500 divided by 9.81. So rho will actually be 764.522, which is actually about 765, right? So 765 is basically my density of the liquid that I want, right? So if you want to put it very accurately, you can actually say it's about what, 7.7. Okay, so if you can also phrase it as 7.7 times 10 to the power of 2, right? So it depends on how you want to phrase your answer. Okay, so the next question, we've been asked to now calculate the new tension of the wire itself, right? So we want to find the new tension when it's now lowered and held stationary. So it's more like this, right? There's now been lowered and held stationary over there. Okay, so how do you calculate the new tension? So first, we introduce a principle of what we call upthrust. So whenever an object gets into a liquid, it displaces a certain volume of that liquid, right? So it causes what we call upthrust to act upwards, right? But it still has its weight that is acting downwards, and there's also the tension, again, that is acting upwards. So we have two forces, tension and upthrust acting up, the weight acting down. So whenever an object enters water, it's going to displace some volume of that water, and that is called upthrust, okay? So how do you find upthrust? So upthrust is actually rho, okay? So the density multiplied by G multiplied by the volume itself, okay? So from my previous question, we had calculated the density of the cylinder itself, okay? So the density of the liquid, we already had it, right? So rho is actually the density of liquid itself. So from the previous equation, we've calculated our density, our value of rho, to actually be 7 point, right? It's about 760, or it's about 700 and, okay, let's just say 765 multiplied by 9.81, right? How do you find the volume? Or the volume of an object, the area multiplied by the length, right? So the area, 3.7 times 10 to the power of -4. The length is 4.0 times 10 to the power of -2. So that gives you a value of upthrust of actually 0.111 newtons, right? So that's the value of your upthrust. But remember, like I've said, the upthrust and tension all are fighting against the weight. So for stationary, means that there's no resultant force. So those two are in conflict, and the value of our new tension will actually be equivalent to the weight minus the upthrust, right? So it's 0.53 separate 0.11. That gives you a total of 0.419, which is 0.42. What are they looking for? They're looking for this formula, and they're looking for your final answer, where you subtract all these two and you get what you want, right? So what is happening here? The tension is actually reducing. So as we lower the object into the water, the upthrust is going to say to the tension, okay, I'll help you with some of this weight so that we can carry this weight together. So the upthrust will help release the tension, right, from the tension itself, so that it is responsible for a small portion of the weight that it once had. So the new tension is going to be less, it's going to be 0.42. Previously it was 0.53. Where did all that tension that the tension was having go? Well, all of it went to the upthrust. Right? So the upthrust is now carrying 0.11, the tension takes 0.43, and the two fight against the weight acting downwards, and the object is in equilibrium. Okay, moving on to question number 5. We've given an electromagnetic wave that is a wavelength of 8.4 times 10 to the power of -6. And we're asked to state the principal region of the EM spectrum that this wave belongs to. So if you look at your right, you see all the wavelengths that you will need. But I really encourage that you find a way to memorize this. You have your textbook. If you don't, look at the internet and find different frequencies that are there. The question papers will also help you find the actual true frequencies that will be there. But as you can see here, the region that has that frequency is actually the infrared. Okay, the next question, we've been asked to calculate the frequency in terahertz, right? The frequency in terahertz. So very important. We know that V is equals to F lambda, okay? But we've been given the wavelength and we want to find this frequency. So frequency is V over lambda. What is the speed of an electromagnetic wave? Well, electromagnetic waves travel at the speed of light. So this is basically 3.0 times 10 to the power of 8. Right? If you've forgotten this, or rather if you don't remember it, I'd highly encourage you go back to these formulas, right? So they usually give you this speed of light in free space, 3.0 times 10 to the power of 8, right? So basically this is the same speed that these waves move at. So I'd highly encourage that you use that, okay? So if we divide this by the wavelength, which is 8.4 times 10 to the power of -6, that gives you a frequency of about 3.57 times 10 to the power of 13, right? Again, tera just basically means 10 to the power of 12, right? So if we divide by 10 to the power of 12, so I really advise you look at all these different prefixes that I've put here so that you can be able to understand what each and one every means. So this is basically tera, and tera is actually equivalent to, therefore, 35.7. So that's basically 36, right? So it's to 2SF, right? That's basically 36, okay? Next, an arrangement that uses a double slit to demonstrate interference has been shown, okay? So given interference pattern of bright fringes and dark fringes that has been formed, right? On the screen across 8 fringes is 22 millimeters, right? So the first question asks us to explain what is meant by coherent, right? Coherent basically means that there is a constant phase difference, okay? So there's a constant phase difference between the waves, right? So between the waves, right? So what does it mean to say they're coherent? It means that the amount by which they're lagging or leading behind each other has to be constant throughout. What does it look like if waves are not coherent? Well, look at this, right? If you have a wave that's moving here, right? And you have another wave that's moving like that, like that, right? They're not really coherent. They don't have a phase difference, right? That's coherent, because if you look at here, the way these are lagging and the way these are lagging are different, right? But if you have waves, you know, that is smooth like that, the other one actually follows, right, like that, we say they have at least, right, a constant phase difference, right? If you find two particles, they'll have the same phase difference across throughout. So basically that is what it means to say particles are coherent. The amount they lead or lag one another has to remain constant throughout. The next question, we've been asked to calculate the separation A of the fringes, right? So whenever you see these questions of double slit experiments, right, I would highly encourage that you just know this formula. Lambda is equal to AX over D. So if you have this formula, always label, or rather list all the things that you're given, right? Are we given lambda? We're given lambda to be 6.2 times 10 to the power of negative 7, right? Are we given the value of D? The value of D is actually 2.8. Are we given the value of X? Well, X is actually the distance between two bright fringes, okay? So we have two bright fringes over here, right? We have one bright fringe, which is actually, if you think about it, is actually from here to here, right? So from here to here, we have one bright fringe over here, right? So this area, basically one bright fringe is covering this area. So this is from one bright fringe to another. If we were to go here, another bright fringe, so we have two, okay? If we were to go here, right, another one here, right, so it's 1, 2, right, so we have 3. If we were to go here, that's 4, 5, right, you get the idea, right? So we're looking at the distance 6, okay, the last one 7, and the last one over here, that'll be 8, right? So basically we have 8 intervals, right? 8 bright to bright fringes, so we have 8 values of X, right? So this is basically 8X. So how do you find X? Well, X will be 22 divided by 8, right? So basically that is how we'll find the value of X. So if we were to go here, the value of X will actually be 22 times 10 to the power of negative 3, because it's milli divided by 8. So how do you find the value of A? A will be d lambda divided by X. Okay, we already have the value of lambda. So A will be 6.2 times 10 to the power of negative 7 times 2.8 divided by 2.75 times 10 to the power of negative 3. So that is the value of X. We've already calculated it. And the value of A would therefore be 6.31 times 10 to the power of negative 4. So the answer will be 6.3 times 10 to the power of negative 4. Okay, so fringe P is the central bright fringe, and fringe Q and R are the nearest dark fringes, and the nearest bright fringe, respective to the right of fringe P, is as shown, right? So we have this scenario here, right? So we have fringe P, okay? We have fringe P and so we've been told by our question that fringe P is the central bright fringe, right? So this fringe here, right, is the central, okay, central bright fringe, right? Very important. And we've been told that fringe Q and R are the nearest dark fringe and the nearest bright fringe, right, to the right. So fringe Q is actually a dark fringe, right? So this is dark, and fringe R is actually a bright fringe, right? So we've been asked to find the difference, the path difference from each slit to the center of fringe Q. Okay, so we've been asked to find that path difference. Okay, so what does path difference mean? Well, path difference basically means if I have a central bright fringe here, let's assume this, let's do on this diagram, right? So if this is the value of P, right, a wave is going to come here and it's going to come over there. Another wave is going to come there and it's going to come over there, right? But if I have point Q, this wave is going to come over there and that wave is going to come there. But one wave is traveled longer than the other wave. For example, this wave has actually traveled longer. If you look at this, it has traveled longer to reach point Q, meaning that the path there's going to be a path difference between these two distances, right? An example that I would like to give you is, consider if you have a house, right? You have two people, one moving at that, one at that angle, and the other one at that point, right? Remember, if both of them are equal distances from a house that is over there, they're going to travel the path that is the same. So they have no path difference from moving to the house. But the house was positioned to that. It's more inclined to person A. So person B is going to travel longer. and there's going to be a difference in their paths. That is what we call path difference, right? So if we look at this example, this diagram itself, right? Whenever you move, so you just have to know this, whenever you move from the bright fringe, the path difference becomes lambda at the next bright fringe, lambda over 2 at the next dark fringe, and so on, right? What do I mean by this? Well, imagine if you have a bright fringe over here, right? The central bright fringe, right? The path difference is 0. Remember, if you go to dark fringe, it will be lambda over 2, right? If you go to a bright fringe, it will be lambda. Another dark fringe, it will be 3 over 2 lambda, right? So whenever we have a dark fringe, it's lambda over 2. It always increases by half, by half, by half. When you get to a bright fringe, it's lambda, a dark fringe, 3 over 2 lambda, another bright fringe, 2 lambda. We keep on going and going and going until we reach 10 lambda, right? We keep on going. So immediately as we reach the dark fringe, that is right after the central bright fringe, the path difference, right, has to be lambda over 2. But what's my value of lambda? 6.2 times 10 to the power of negative 7 divided by 2. That gives me my value of 3.1. Okay, 3.1 times 10 to the power of negative 7. So my path difference will be 3.1 times 10 to the power of negative 7. Remember, the path difference is basically how far does one light travel from one slit to the other slit versus the path traveled by the other slit. Again, the last one, state the phase difference between the light waves meeting at the center of fringe R. So a fringe R, that would be over here, right? So if we're to analyze our situation, right? If we're looking at fringe R, right? So we have fringe P, which is at the middle, fringe Q, and then fringe R, right? Again, with phase difference, it's basically simple, right? You first start with 0 and you increase by 180 as you go up and up, right? So the first one, it will be 180, the next one will be 360. So, and you keep on increasing by that multitude. What do I mean by this? Well, imagine you have this thing itself, right? So this is your central bright fringe, it will be 0, right? If you have a dark fringe, it will be 180. If you have a bright fringe, it will be 360. Another dark fringe, it will be 360 plus 180. Another bright fringe, it will be 360 plus 180 plus 180. If you have another bright dark fringe, it will be 360 plus 180 plus 180 plus 180, right? You keep on going and going and going. So a question might have given you R that is about certain fringes away from P. It will keep on increasing by 180, right? So if we had B at Q, first from P to Q is 180, from Q to R is 360. So the first difference is actually 360 degrees. Very important, right? So moving on to the next question, question number 6. Okay, so we've been given a metal wire in a circuit that is this length, right, and the cross-sectional area of that. So the total number of free electrons in the wire is actually 2.3, right? And we've been asked to show that the number density of the free electrons is actually 8.5. So what is the number density? Well, the number density is actually the number of charge carriers per unit volume. Do we have the number of charge carriers? Well, it's 2.3 times 10 to the power of 23. Do we have the volume? Well, volume is actually area times length, right? Just 1.5 times 10 to the power of negative 6 times 1.8. So that gives you 8.5 times 10 to the power of 28 m to the power of negative 3, right? M to the power of negative 3 basically means per cubic meter. Calculate the average drift speed of the free electrons, right? So we know that I is equals to ANVQ, right? You can look back at your data formula booklet if you've forgotten this equation, but basically we just want to find the value of V. So V will be I over ANQ, okay? So what is my value of I? My I is basically my current, right? So what is my value of I, right? But current is actually charge per unit time, right? So if I want to find my current, do I have my charge? Yes. Do I have my time? 2.5 minutes, right? So I basically say 172, okay, divided by 2.5 minutes times 60, right? Which is actually the time that is going to come, right? So like that. So that is basically my value of V, right? So my value of V will basically be 172 divided by 2.5 times 60, okay? What is my value of A, which is my area? 1.5 times 10 to the power of negative 6 times N, which is 8.5, times 10 to the power of 28, times Q, which is 1.6 times 10 to the power of negative 19. Rather, I highly recommend that you break down these calculations. First, find the value of I separately, then find these different questions, right? You can even store them in your calculator so that you get a value of V that is as accurate as possible as it can possibly be. And your answer becomes 5.6 times 10 to the power of negative 5. So it's 5.6 times 10 to the power of negative 5. Remember, solve the question, know the formula, and then you apply. So what are they looking for? So they're looking for a person who knows this whole equation. So this whole process that we have done from here to here is worth 1 mark. And us knowing that this is true is actually equivalent to 1 mark, right? And the answer is equivalent to 1 mark. Similar to here, the fact that we just know all of that is actually 1 mark because we already know what number density is, the number of electrons per unit volume. Okay, moving on to question number 7. We're almost done. This is our last question for electricity. We've been given the fixed resistors with that resistor and that resistor, and we've been asked to calculate the current in the resistor of 5,800 ohms. Okay, so how do we find the current, right? So how do we think about this? Well, current is actually equivalent to, right? So current is actually equivalent to voltage over resistance, right? So we have the resistance, which is actually 5,800. So how do we find the voltage across that particular component that we have? So the reading across this voltmeter is actually 6,000 volts, right? So I would highly recommend that, okay, we can redraw this voltmeter so it looks much more like something that we're used to. So like that. So basically this reads 6 volts, right? So try to redraw these things into something that you can understand. So electrons are very clever. So they're going to come and they're going to reach this particular point and they're going to give a certain energy to the first resistor and a certain amount of energy to the other resistor. And according to our calculation, the total energy is going to be 6 volts. So by the time they reach here, so if they were here, they had 9.6 volts, right? By the time they reach here, they actually have 9.6 minus 6.0. And that is all that they're giving to this particular resistor itself, right? So the current here will actually be 9.6 subtract 6.0 divided by 5,800. And that gives you a total current of 6.2, okay, times 10 to the power of negative 4. So 6.2 times 10 to the power of negative 4. Moving on to the next question. Okay, so we've been asked to calculate the resistance of the thermistor. So how do you find the resistance of the thermistor? Well, we know that V is equivalent to IR. Okay, so the voltage across this thermistor will therefore be equivalent to V times IR. But you now have the current for the whole circuit, right? So the current across the 5,800 will be true for the current across the whole resistor itself. Okay, so if we look for the voltage across that resistor itself, right? So the voltage across the 3,400 will actually be 3,400 times 6.2 times 10 to the power of negative 4. So that gives us about 2.11 volts, right? So this one will take 2.11 volts, meaning that that one will take the remainder, right? So V across the thermistor will actually be 6 minus 2.11. That is actually 3.89 volts, right? But resistance is actually voltage divided by that current, right? So 3.89 divided by 6.2 times 10 to the power of negative 4. That gives us a total of 6,270 ohms, right? So that's basically 6.3 times 10 to the power of 3. So remember, what is your voltage across this one, right? So once you have calculated that, you can then find the voltage across the thermistor, then you can find the resistance across the thermistor, then you can find anything that you want in the question. Okay, moving to question number C. the initial energy that is stored in the battery is 2.6. Assume that EMF is constant, right? Determine the final energy stored in the battery after a charge of 330 has moved through it, right? Remember, we know that energy, right, is equivalent to the EMF multiplied by the charge Q that passes, right? So the EMF that is there is 9.6, right? So the EMF is actually 9.6. So if we have 330 passing, that means the energy that they have is 3.2 times 10 to the power of 3 joules, right? So if electrons come with a charge of 330, they're taking away 3.3 times 10 to the power of 3 joules. So how much energy remains, right? So basically, the energy that remains, okay, will be equivalent to 2.6, okay? So we have 2.6 times 10 to the power of 4, subtract 3.2, okay, times 10 to the power of 3. And that gives you a total of 2.3 times 10 to the power of 4. So that's 2.3 times 10 to the power of 4. So always remember, what energy are you given to begin with, right? 2.6 times 10 to the power of 4. Electrons come with a certain charge. They take away a certain amount of energy. What amount of energy remains? So you can find the energy that is remaining, and you can find the energy that remains by subtracting it from the initial. So it's final minus initial, which is the energy that is stored in the battery itself. Okay, so the environmental conditions change causes an increase in the resistance of the thermistor itself. And if you can also state whether there's an increase, a decrease, or no change to the temperature of the thermistor. Okay, so a thermistor almost operates in a similar way to an LDR, right? The way that the resistance changes, right? So it's more like that. The graph is basically like that, right? So this represents cold, right? And this represents hot, right? So if you're at very hot conditions, your resistance is very low, right? But it's very cold, your resistance is actually high. So basically, this is how a thermistor works, right? Whenever it's hot, so this is called negative temperature coefficient. Whenever the temperature is very hot, very low resistance. Whenever the temperature is very cold, very high resistance, right? So if I have an increase in the resistance of a thermistor, what does that tell me? Oh, it's very cold because the resistance has actually increased. So that would mean that the temperature has actually decreased, right? So the temperature decreases in order for the resistance to be high, right? And then they ask me the current in the thermistor. Okay, what happens to the current in the thermistor? Well, if the resistance actually increases, right? What happens to the current? Well, I know that V is equals to IR, okay? Mean that resistance is actually inversely proportional to the current, right? If the resistance increases, the current has to decrease, right? So the current in the thermistor actually decreases, okay? The potential difference across the thermistor. Now, if the thermistor has a greater resistance, electrons, as they arrive here and they're about to enter into the thermistor, they acknowledge that this thermistor has a higher resistance than before, right? So the resistance across this has increased, right? So the resistance has increased, right? So electrons will give more energy towards this resistor itself because it is so much resistance, right? So they have to be very lenient towards the way they give their energy. So if you're looking at everything here, the potential difference across the thermistor has to increase. Why? Because it has a greater potential difference. So it has to have a greater, it has a greater resistance, sorry. So it needs a greater potential difference. Okay. Moving on to our last question, which is atomic physics. Okay, so our last question, which is particle physics or atomic physics. Okay, so let's get to it. We're given an isolated stationary nucleus X that emits an alpha particle to form a nucleus Y. So let's write out what's happening. So we have alpha decay that is occurring, right? So it's alpha decay. So you have a nucleus X, right? So it's A and Z that decays to form Y. A minus 4, Z minus 2, right? So it gives out that alpha particle, okay? That alpha particle, right? So we've been asked to compare the number of protons in each neutron, in each nucleus of both X and Y, and state and explain whether the charge of nucleus X is less or greater than the charge of nucleus Z. So nucleus Y and Z are isotopes. So remember, it's the charge of nucleus Y that we're mainly concerned about, right? So is it less than, greater than, or the same as the charge of that? Well, it's the same, but why? Because it allows us to state and explain. Well, since nucleus isotopes basically have the same number of protons, right? So since they have equal number of protons, right? Nucleus Y and Z have the same charge, right? Very important. Comparing nucleus Z, right? If it has undergone alpha decay, what happens? It loses 2 protons, right? So an alpha particle basically consists of 2 protons, right, and 2 neutrons in its nucleus, right? So if you have an atom X that loses all of that, meaning that it actually loses 2 protons, so its charge decreases by 2, right? Because it's actually losing electrons, right? Sorry, protons, right? So because it's actually losing protons, right? So nucleus X actually has so Y has fewer protons, okay, than X, right? By how much? By 2, right? So what does that mean? So Y has a lesser charge than X, right? Very important. Using the principle of conservation of momentum, explain why nucleus Y cannot be stationary immediately after decay of the nucleus, right? So if you have nucleus X, right? So if you have nucleus Y, right, like that, if it decays and it forms this nucleus X and that alpha particle that are emitted in those directions, right? This cannot remain at stationary. Why? Because the total momentum, right? So the total momentum, okay, after decay, right, must be 0. That must be the same, right? So before decay must be equal to after decay. So Y must have an equal and opposite moment to that alpha particle. Okay, so Y must have an equal, okay, and opposite momentum, right, to the alpha particle. Okay, hence it cannot remain stationary. Okay, so what are they looking for? They're looking for the alpha particle that remains. Okay, so total momentum after decay must be 0. Therefore, Y must have an equal and opposite momentum to the alpha particle. Hence, it cannot remain stationary. So this is the second mark that you'll be getting. The first mark that you should get is that the total, okay, so the total momentum, before decay, right, before decay is 0. And, right, so this is again the first mark that you get. So the first mark that you get, you first say that the total momentum before decay is 0. Okay, so the total momentum after decay must be 0. So if the alpha particle moves in a certain direction, Y cannot remain stationary. It has to also have an equal and opposite momentum to that alpha particle. So it's going to move in a certain direction so that that momentum is the same before as well as it is after the decay. Okay, so thank you guys for watching. This brings me to the end of this paper. I hope you enjoyed it, and if you have any comments, queries, or any thing that you found unclear, please comment so that I can improve. Thank you. I'll see you in the next one.